Okay, this is a short video on stress and strain. It's a little bit of revision for stress and strain, and it's also bringing up a point that I didn't raise when we covered this topic. And it's something that you may need. It will certainly need it for your HSC. So we're going to look at, and maybe for your preliminary exam, we're going to look at in our braking systems today, stress and strain. This is a really important area of engineering because it's where we test materials to see how much force they can have applied to them before they fracture. And we covered this formula here, force over area, where you actually stretch a metal bar. And we talked about that down here. So you've got your metal bar here, and you're stretching it. And you can see that as it's stretched, it starts to what's known as neck down before it fractures. So if we look at this graph here on the page, this is a really important graph. You really need to get your head around what's happening here. And this is a graph that shows what's known as a yield point phenomenon, and that's where you have an upper and a lower yield point. You don't always have that. I'll talk about that with you later in class. But for this instance, you do have that phenomenon, and you've got all these things happening. You need to know what all of these things mean. So where this actually starts to dip down here, that happens even though you're applying more and more force. You'd expect this to just keep going up and up and up. But the reason why it reduces is because the material starts to neck down, okay, where the diameter starts to reduce quite significantly. And that's why you get that feature in the graph, that necking down. If it doesn't neck down, it will just break, and you won't get that dipping down. So if you're asked if a material is necked down and you've got a graph where it doesn't do this little movement downwards, you'll know it hasn't necked down. And you've also got various areas in this graph. Here they've got the elastic point. So elastic area of the graph here means that if you were to let go anywhere in this area here when you apply a stress force on this, when you apply a force or a load on this and the stress is created, as long as you don't go past this point here in stress, your material will bounce back. Once you go past this point here, the elastic limit, the material will no longer bounce back. And there's a small distance between this point and this point. Proportional limit means that your stress and your strain are a straight line. Once you go past that proportional limit, the stress and strain are no longer straight, but the material is still elastic. It will still bounce back. But once you go past that elastic limit, you've deformed the material. Now the upper yield point is where you're applying more stress, it's a turning point in this graph, okay? So you need to know in a material that has yield point phenomenon, you've got an upper yield point and a lower yield point. Okay? You need to be able to identify those things. Okay, so for this question here, or for this discussion, I'm going to have two videos. I'm going to have this video explaining these formulas, okay? So basically, we've already used the first formula here, force over area, and the area is the initial cross-section. So it's before you apply the stress to the material, it's the area when it hasn't changed, okay? So you might, even though you're applying a force, and you can see that as you apply this force, when it fails, the cross-sectional area, if you were to cut through this bar here, on this top bar where it's broken, it would be a lot narrower than this one, okay? But for our normal engineered stress or engineering stress, we're dealing with the initial area before we stretched it, okay? So that's the main thing you need to remember, and the units are in Newton meters to the -2 or pascals, okay? Whichever you prefer or whichever they're asking for in the question. Now, engineering strain is E over L naught. So L naught is the original length, as in starting from 0, okay? So L naught for this particular question here would be this bar here before we stretched it, okay? Once we stretch it, we've got a new length, okay? It's increased in length. So for engineering strain, what we do is we take the extension, which is the change in length, and we put it over the original length. So if we had a bar that was 200 millimeters long, and when it broke it was 210 millimeters long, we would put the extra 10 millimeters on top, which is delta L, the change in length, and we put the 10 over the 200, okay? Now you don't have units for this because it is a ratio, okay? The units cancel out, so length over length. Now you don't need to convert your units as long as both units are the same, okay? Because it's a ratio. If you have millimeters over millimeters or meters over meters, you'll get the same answer, Okay, so that is engineering stress and engineering strain, exactly what we covered in class, but we were just talking about stress and strain. These are actually more precisely termed engineering stress and engineering strain. Okay, so then we've got this new idea which is called true stress and true strain. Now, true stress is really, really simple. All it is the force that's applied, just like you did in the engineering stress formula. So force applied, exactly the same, but instead of putting it over the area of the bar before it is stretched, you're putting it over the area at the instant it breaks. That's what that little I stands for, A with a small subscript of an I, the instant that it breaks. The area at the instant it breaks. So for this situation here, if you were working out engineering stress, it would be the force applied over the cross section of this bar before you actually stretch it. And if you were working out the true stress, it would be the force applied, so it's the same force value, but you, instead of dividing by this area of the bottom bar, the original area, you would be dividing by this smaller area, okay, just before it breaks. Okay, so that is the difference. So you will normally find that your true stress is going to be a greater value because your denominator in your fraction, when you work it out, will be smaller. Okay, so true stress is normally going to be a higher value when you calculate it. And then true strain, that's a little bit harder. Okay, so they give you a formula here, or I've given you a formula here. Instead of putting the change in length over the original length, what you do is you put the longer length over the original length. So you're not dealing with a change in length, you're dealing with the longer length. So then the longer length would be, in this instance here, this length from here to here, over the shorter length, the original length, and you take the natural logarithm, okay, of that value, ln, not log on your calculator, ln on your calculator. And that's how you calculate those values. I'm going to do a question now so that you get a better understanding of the difference between our engineered stress and strain and our true stress and strain. We'll do a question, so we'll see how this all works. See you in the next video.